What about him?
Oh shit! All right. Looks like nobody's online.
Well, I spent 4 hours.
Then let's just adjust the camera.
Spent 3 hours on one.
I hope this is okay.
I'm talking about just quit.
All right.
Oh no, I'm talking about.
So nobody's online. That means this is just a recording of the lecture. So I hope you guys know that you have access to the recorded contents of the lecture. So if you don't understand any of it, you can go back and always review. You don't have to see the whole thing from start to end. You can just skip forward and go right into the point that you missed. Okay? So it's already been recorded, and then nobody's online today. That's good. So let me just start sharing my desktop to begin with. Okay, good. All right. So, okay. So we're going to continue on Unit 3, and then this week I tried to sort of slow down my pace of covering. We talked about continuity. We talked about conservation of linear momentum, and we talked about Euler's equation, and we talked about Bernoulli's equation. Then I think you feel like, hey, wait a minute, we got stuck. Because Bernoulli is so limited. And where do we go next? And then that's where we are, I hope. Okay, so we're going to pick up from there today. So before we forget, we're going to start taking today's in-class attendance. Then we're going to move on, okay? This is what PM. Okay, so this is your question. Oh, 1 o'clock sharp. Great. So let me close the door. Hopefully nobody's going to get in. Then let's just take attendance. Ready to go? You have a paper? I hope so. Is this a real paper or just a simulated screen? It's so cool. Anyway, I love that. Okay. Right. So yeah. Anthony, all right, so this is the class. Everybody's here except a few Air Force people attending at that conference. Silver wings, something like that. And then this is just an informal announcement, but if you want to attend online ride when you are away, go ahead and try. I mean, I don't mind. You can always access to the recorded lecture, but you can at least try to attend online when you are moving in airplane or something. I mean, yeah, you can always attend online. Online ride is probably better than just watching video later, because watching video is like the University of Phoenix. This is not it. Okay. All right. So today, I think let's just take a look at updates today. So obviously, you turned in quiz 3, and then I corrected it this time. I didn't forget. I took your quiz 3 about 12:30-ish. I tried to be honest. About 12:30, I realized, wait a minute, there's something to do. I remember that. So I took it 12:30. So still like at 12:30, but not like a 3:50 like last week. I completely forgot about taking your due 12 noon, but I kind of started to teach the class 1 o'clock without knowing, hey, wait a minute, today something was due. At least today I remembered, so. And then something new here. I announced on Saturday, and then I hope you're aware that you can create your own project group or team. A project phase 1 is coming up. So you're going to create your own group, maximum 4 students, total 6 groups. You can freely sign up using Canvas. Let's just take a look at it today, okay? So I already logged in to Ernie. Then I can go to Canvas. Here we go. So this is Canvas. And then since I'm an instructor, so the view is slightly different than yours. Yours is student view. Mine is instructor's view. This is section 3. So if you click on that, you can go visit people right here. And then project P1 team, this is now active. I activated it. So this is project P1 team. You can freely sign up and create your own team, total 6 groups. There are a few people already signed up. Project phase 1 team 1, who are those? Anthony and Ji-Chan, right?
Yeah.
You guys signed up already. You're sitting next to each other, already acting like a team. That's fine, no problem. And then who's one person signed up team 3? Ismail, okay. Well,
We are yet to join.
well, do you want to do it now? I can
Please.
drop in Kaidi and then
Can you add me with the first group?
If you want to add Hunter to it, that's best.
okay, anyways,
Yes.
I'm not gonna do it. Anyways,
Okay.
it's because I'm gonna trigger the chaos. No, you can do it. The bottom line is, you can do it. Please do it. That's what the announcement says. I'm not gonna do it. I added Kaidi, but I'm gonna push it back, sorry. Because you have to do it. Yeah.
Once we add ourselves to a group, we're done. We don't have to.
Well, I'm gonna rock it.
Yeah.
12 noon Friday this week. I'm gonna rock it. You mean rock it? That means I'm gonna deactivate it so that you can no longer touch anything. Group is formed. If your name is not on, you are not gonna do any project.
If we sign up for a group prior to 12 on Friday, we can still move around until
Until Friday noon.
Okay, so it's not locked until the end of the week.
I'm gonna rock it 12 noon
Okay,
on Friday.
got it.
So over the weekend, this weekend, you're done, you're rocked. If you don't sign up, you don't work on the phase 1 of the project. Very simple. So you're going to spend this week trying to find your best partner. Probably rather than just drop my name, not knowing who's gonna show up here. You probably need stars, don't you? Possible. I guess you guys probably are doing it already, but yeah. Before somebody drops the name here, that could be completely strange. I don't know. If you need to fill up that 4 people that you know and comfortable, I don't know the group dynamics. I'm not gonna take care of any of those. Like I said, okay? Because I'm too busy for that. I'm not like a nursery worker. Let me teach, okay? So that's why team formation is all yours. If you hate each other, just hate each other until the end. That's fine. Just to produce something out of that hatred. I'm okay with it. So, look at that team 4. It's already full. Who's that? Those people. No problem. Okay, no problem. Sure, no problem. So this team 4 is already formed. It's a 4. I'm not going to welcome anybody else. That's where you are basically saying. So please do this week. You have plenty of time until Friday noon. Okay. So this is phase 1 of the project. So you're going to start working on it. Now you have to, of course, take a look at the instructions of phase 1 of the project. This is already posted. Please read through it. Okay. Lots of details. I'm not gonna, well, you know me, I'm not gonna give you any partial credit if you do something different or wrong. I'm not gonna do that. So please read through the document. That's probably the first job as a team. And let's just get together, read together, maybe read together remotely online using Team and whatever, whatnot too. You can do whatever you want to. Since this is under a very weird situation right now, COVID, but you can still need to learn how to work remotely as an effective team. That's also another skill set you can pick it up under this tough situation. So I would emphasize, okay? So please pick up the social networking or other means or methods to effectively get connected, communicate, work together, share the files, double check as a team. Now is the time you can take this as an opportunity to get extra skill sets. Okay? All right, any question about this? I hope everything is crystal clear. So this week I'm going to kind of go through because I want to spend some time going over thermodynamics. Some of you have already done thermodynamics. Some of you are taking thermodynamics together with this course, whatever it is. Thermodynamics is quite important for aerodynamics. Not for this class, I have to say, because this class is all about theoretical low-speed aerodynamics. Now, if you're talking about theoretical low-speed aerodynamics, what usually happens is people just completely forget about thermal. If you go do a low-speed wind tunnel testing, people never speak one thing. And well, have you ever heard of people talking about this in front of wind tunnel low speed? That is the temperature. Nobody seems to care about the temperature of here, temperature of there within the low speed wind tunnel. They assume temperature, huh? It's a room temperature. What are you talking about? It never change. What do you mean by that, by saying that statement? Well, I'm not going to even talk about thermodynamics. Thermodynamics, I don't even consider that. So that's what you've been doing so far, up to this point. So based off of that idea, you still have one tool, right? One tool only though. What is that tool you love to pick up and use? That's called Bernoulli's equation, right? That's right. Because Euler's equation is not the tool. It's a differential equation. You have to do something. You have to integrate to get some meaningful result. This is one meaningful result. That's called Bernoulli's equation, right? So Bernoulli's equation says P plus 1/2 rho B squared. Let's say location 1. So this is a streamline, this is the location 1, this is the location 2. You can apply actually Euler's equation along the streamline, then you can integrate between the location 1 and 2 in the direction tangent to the path. Then you come up with the Bernoulli's equation you can apply between location 1 and 2. So this is the equation. Now I purposefully setting rho because rho is, what is this rho? Density here, density there, no matter what it is. I don't know if it could be standard sea level density or could be some different density within the wind tunnel. We never know, but those will stay constant because Mach number is less than 0.3 incompressible. That means density doesn't change. That is the condition for Bernoulli's equation. Now our situation shows up. What if the Mach number becomes 0.300001? That is quiz 0 problem 3, wasn't it? Please speak up. Somebody actually did the quiz 0 problem 3, and that was the situation, wasn't it?
That was a different, it was 4.
4. Okay, 4. Yeah, okay.
Yeah.
4. That's right. Quiz 3 is nothing. Well, quiz 3 is nothing. You did it.
Yeah,
Right?
'cause-
Yeah,
yeah,
we did
'cause
quiz
you scared me.
Sorry.
You scared me.
Sorry. You don't have to.
I'm like, I tested the Mach number and it was less than 0.30.
Yeah, that's a quiz 0 problem 4. Well, I'm already talking about quiz 4. That's fine, because quiz 3 is done.
Okay,
Oh my goodness.
Yeah.
Oh, you're done quiz 3.
Yeah.
Let's talk about quiz 4 then. Because your life keeps moving forward, right?
Quiz 4 is a problem with the Mach number, unfortunately.
So quiz 0 problem 4 Oh, what is the Mach number? Oh my goodness, 0.30 something. Holy cow, what should I do? Did I do right? No. Let's just round it out, round off to 0.3 and hoping that the professor doesn't catch up. And then, oh my goodness, I got 0 out of 10. 0 out of 10 is like a joke, right? We can laugh at it in here. But when you try to get a real job, when you try to graduate, get a real job, the dream job, that's going to make a difference, right? I wanted to be always working. I wanted to work with this company. By the way, I have one student who stopped at my research lab last week. He said, hey, Dr. H, I'm not going to graduate another year. My graduation is next year this time around, but I already got a job. You know what? It's Lockheed Martin. That's the dream job I wanted to work with ever since I was a boy. My goodness. Let's forget. So I want to see every single one of you sitting here getting that experience. Take it seriously about this class and then class coming after this. Engineering is a serious business. The only seriously pursuing that kind of thing, that kind of people can get a real job. If you only want, I want to pass this class, I don't care. Let me just get the hell out of this class as quick as possible. I'm not interested kind of attitude. That kind of job is going to be the only job you can get. So anyways, where am I? I'm almost completely lost anyways. But the Bernoulli's equation, what is the limitation? You go realize like, oh my goodness, quiz 4 or quiz problem 4, I cannot use Bernoulli. Wait a second. I cannot use Bernoulli. Wait a second. What's the problem? Let's just start thinking about it. What's the problem of this Bernoulli? Bernoulli is based on lots of assumptions. First of all, Bernoulli's equation comes from where? Euler's equation. Now, Euler's equation comes from where?
The static equation.
It's coming from
conservation
of linear momentum. Now, that has nothing to do with energy. That means temperature, huh? Temperature is a concept of energy. If you talk about energy, you oftentimes talk about, is temperature high here? Well, because we got more energy here, because I got higher temperature. Or the temperature is lower here, because I got lower energy temperature. Well, within the flow field, we don't even talk about that kind of stuff. That's Bernoulli. At least the form you're looking at right now. So this equation can never be used for high speed, because high speed always, the energy is involved. Right? So we're going to step right in here. Huh? Let's take a look at energy principle. This is the first law of thermodynamics. And then I want to go back to the concept of compressibility. Compressibility is closely linked with energy principle. Do you remember the compressibility we talked about when we talked about the continuity? Compressibility, what the heck is that? So in order to talk about compressibility, I didn't want to use the density. People say density constant, oh yeah, cool, but what does that really mean? Let's use not the density, but something else. Specific volume. This is the 1 kilogram or 1 slug or 1 pound mass of air. Anyways, it's a control mass, okay? So let's assume this is 1 kilogram of mass. I'll give it to you right here, right now. How much volume does it make is called specific volume. So this has a volume. That volume depends on pressure you are in, okay? If you're in a really high pressure zone, the volume is really small. If you are in a low pressure zone where flow is highly accelerated, the volume gets expanded. So shrinking and expansion, shrinking and expansion due to the change of pressure. What is that? from thermodynamics concept. It's called work. What kind of work? Moving boundary work. It's essentially the same as if, have you ever seen in thermodynamics? Same as if you have a piston cylinder configuration, you put the air in and push it or heat it up, expand. Have you ever seen that in thermodynamics? It's a very classic first law of thermodynamics derivation. Let me show you that because I'm ready today. I brought that thermodynamics. Oh, here. This is not there. This is AE301 energy transfer fundamentals. This is basically thermodynamics and heat transfer class I teach for EEs, electrical engineers. They are probably not interested in thermodynamics almost at all. Oh, it's not my major kind of attitude. So I teach thermodynamics for EE folks. It's very challenging because motivation is zero almost. So I have to do something to raise motivation. So I always go down to very down to earth, easy explanation because that's the only thing they want to run. Once I start talking about something difficult, they go like, oh my goodness, I start daydreaming, start thinking about electric circuit instead. So anyways, this is the first law of thermodynamics, the very first encounter. So I want to know what is the equation of first law of thermodynamics. Usually comes from this form, right? Very classic example, piston cylinder configuration, weightless, frictionless, no leak. So this is the piston cylinder. This piston doesn't have any weight, no mass. No mass is not the right form. No weight. There's a mass always, but it's good. Anyway, this is copied 100% from former dean of engineering, so that's his fault. Your grandpa. He said no mass. Wait a minute, no mass? What do you mean? Anyways, no weight is a proper explanation. The gravity is ignored. So weightless and then frictionless, no leak. So this is what do you call this thing? A mass inside of this piston cylinder. What do you call this? Control mass. Here we go. But this is not the unit mass. So there's some kind of physical mass in it of air, but there's no leak. So initially, this mass of air has an energy EI. This is the initial energy content in it. I don't know how much energy in it, but energy content E and initial I. Then all of a sudden, you decided to push this piston down. How would you do that? You're going to add work in. This is W in. So you just add the work, and then energy transfer in due to work, working, or energy input. So as a result, what is the energy contained within this mass? EI plus WN, right? Add it together because you add energy in. That's right. So EI plus WN. So now you're going to push pin in it so that prevent this piston one doesn't move, okay? So push the pin in it. Then you heat up. That means you're going to do a heat transfer Q into the system. You're adding another energy due to heat transfer. So after this, what is the energy content within? EI plus WN plus QN. Yes, of course. Then after that, you're going to remove the pin. The gas expands and then push the piston out. What is that? Work output. Work out. So what is the energy content after that process? EI plus WN plus QN minus W out. Minus W out. Because you take energy content out, right? Do the work. Work transfer out. So next, you're going to again put the pin in. And then you're going to dip everything into the super cold, ice cold water. Then you're going to take the heat energy out. What is that? This is the heat transfer out. So after this process, what is the energy content within? The EI plus WN plus QN minus W out minus Q out. That is final energy content, EF, right? So here is the equation. So if you take the energy difference between initial and final state, that is going to be balanced up against how much energy you transfer due to heat and then work transfer in minus heat and work transfer out. Very simple equation. This is first law of thermodynamics. It basically says energy is balanced. Energy is conserved. What are you talking about? That kind of equation. Yeah. So this is the first law of thermodynamics. This is actually algebraic equation. That's kind of cool. Because you can pick up this equation, plug in, and get the numbers out very easily. Okay, now let's go back to arrow because I kind of teach the arrow a little bit more difficult way. This is not AE, students. So this is first law of thermodynamics for unit mass, which means this is a very, very, very small, tiny mass of air. This is the first law of thermodynamics. Take a look at this equation, and is this the same equation that you saw?
Yeah. It's the sum of the energy.
Sum of the what?
Change in.
This is a transfer due to heat.
Yeah.
This is what?
Change in work.
Transfer due to work. And it together is what?
Sum of energy.
Energy content within the system, which is control mass in this case. Energy is balanced. What are you talking about, kind of equation? Now, so I guess you really need to start thinking about when you see the equation, you have to reason yourself why this equation is in differential form. Why the other equation you saw is just all of a sudden algebraic form. You can pick up and plug in the number and ready to go. This is not. This is the differential form of equation. Why is that? Because you're talking about differential mass. Total mass is very, very small. But this is universally applicable for any size of mass. So if you apply this equation to the piston cylinder, such as I showed you, all of a sudden you get algebraic form of equation. It's the same thing. Yeah. Now here is a hardcore question for today. And then this is actually the question I know at least one occasion or several occasions that the job interview that the people willing to ask. If you take a close look at this equation, this is the first law of thermodynamics. Everybody knows. This is a dE. This is what?
Delta.
Delta Q. This is delta W. Why do you need to use delta here and then D here? Why? Well,
I think that's the derivative of the normal equation that we calculated earlier.
no. Thank you for your attempt, but no. Go ahead.
You have to add a significant change of work and heat to get a small change of energy?
No.
Okay.
Thank you for your attempt. Anybody else? Go ahead, try. Because this could be a real question. This actually reveals how much do you really understand the concept of thermodynamics or not. This is a very fundamental question, but lots of people fail. Lots of people. Last semester, I did the same thing in aero. No one was right. Go ahead.
Could it be like energy is over time, or it's like a derivative of time where the other ones just change? And
No.
change time?
No. Anybody else? Go ahead.
Your energy can be positive, negative, so there's no like a delta.
No. Anybody else? Go ahead.
Does it have to deal with the control?
No. Yeah, this is a control mass equation. Yeah, go ahead.
The differential is exact, but the delta depends on how you get there.
Ooh, probably give you 6 out of 10. Very close. Let's just take a look at today. I have another. Well, I don't blame you because I didn't even know when Dr. Felton told me that. I was teaching Samo, and then one day, former dean of engineering said, "Hey, Skil, do you know the difference for those?" I said, kind of. Well, let me tell you what it is. I ended up talking 1 hour with him, and now I realized, well, I was stupid. Maybe I shouldn't have taught this Samo class. I regret to death. But anyways, let's take a look at updates page. So I don't blame you, any of you, okay? Because even professor who was teaching thermodynamics didn't know before I met his grandpa. So let's take a look at this thing. Control mass analysis, that's what you saw. So this is the typical control mass analysis piston cylinder configuration. People use that as a first step for first law of thermodynamics. This is a very classic example. Now, as you push this piston cylinder, there are a variety of ways to push. You can push it like this, or you can push it very slowly, or you can push it and slow down, or you gradually push it really hard toward the end. You can push a variety of ways. That's called the process pass. So the amount of the work you can get depends on the pass you take. This is called process-dependent variable. Work is one of those. Similarly, the heat transfer is also that kind of thing. Process-dependent. So if you can take process like this, or process like that, process like linear process, amount of work you transfer is essentially area you can create under the process pass. So that area is going to be different value. That's why you cannot exactly differentiate. So you have to take small, tiny, infinitesimal amount of change, one thing at a time. And then you have to know the full detail of the process pass in order to finish up this integration. That's why. Process-dependent variable. That's what the heat transfer and work is all about. This is so fundamental in thermodynamics, yet people don't realize. So this is delta, right? This is the moving boundary work. It's a classic example of thermodynamics. You have a piston cylinder. You push it to add the work. You expand and get the work out. Okay? That is delta always. Why? Because it depends on the process pass. Look at this. So moving boundary work. So this is volume 1, volume 2. So this is larger volume, this is smaller volume. So this is compression process, isn't it? Because larger volume to this is the expansion process. Right? A smaller volume to bigger volume. It's an expansion process. It depends on how you expand. It's going to produce different value of work output, of course. You can expand linearly from 1 to 2, like a pass B. As a result, 8 kilojoule of work you can produce. But if you expand from 1 to 2 in the pass C, you can only get 5 kilojoule. If you expand from 1 to 2 with the pass A actually produces 10 kilojoule. So it all depends on how you expand. Process is involved. So you have to know the detail of the process in order to get actual amount of work transfer you can get. That's why we need to be very carefully. I'm not going to put the dW. I'm going to put the delta W. So in order to finish up that integral, you have to know the process pass as an at least mathematical form. I hope this is what you did in thermodynamics. And then I hope this is what you're going to do in therm. Okay, so stay focused on that fundamental concept. Heat and work transfer depends on the process pass. So in order to accurately predict the amount of energy you can transfer, you have to know what kind of process involved. So that is actually a big subject of thermodynamics. So thermodynamics, you spend quite significant amount of time trying to find out what kind of process is involved, right? Of course, because each process creates a different amount of transfer of energy. Okay? So this is, if you answer like this, you probably get a dream job, right, at your job interview. So keep that in mind. Those are the kind of things people want from you, not the plug and check. Plug and check, people probably go out in the street and get people and hire with a minimum wage because anybody can do it. You are engineers. Okay? Let's try to be an engineer. That's going to make a huge difference with the people outside of this classroom. Okay. All right. So that is first law of thermodynamics. So obviously, equation itself is very simply tell that energy added or subtracted due to heat or work transfer is going to be balanced up against the internal energy you are going to store inside of this 1 kilogram of air, which is small tiny air, control mass. So how much energy you can store inside depends on how much energy you transfer in and out due to heat and due to work. Now, if you have more energy inside of this small tiny kilogram of mass, what do you see is going to happen? Temperature goes up. That means you store higher energy. But how much energy can you store inside of this 1 kilogram of mass of air? That is a big question. That's called the specific heat. That is the specific heat. How much energy you can store inside of this much mass of air? That's called the specific heat. Heat content within this small tiny mass. So that actually comes into play, very important term, specific heat, okay? So next page. So let's just go back into, once again, this small tiny control mass making up this much volume called specific volume lowercase b. So what is the volume of this 1 kilogram of air? It's called lowercase b, specific volume. So that volume is going to change, expand or shrink, depending on the pressure you have. That means work is involved, don't you think? That's the only work we are going to consider for a moment in aerodynamics. Because if you're looking at the flow field, air is flowing, what kind of work do you expect? This is the only work you would expect. And then this is the only work you're going to start thinking about only if the flow field is high speed, where this kind of activity is becoming significant. What do you call that? Compressibility. Okay. So now in high speed, you begin thinking about, hey, this is a compressible flow field. What do you mean? This kind of thing always happens. That means, hey, work is involved. Work involved means, hey, energy level changes within each control mass of air. Energy level changes. Sure. You take energy in or you take energy out for each one of those control mass of the flow field. So this is the work. Okay? So today, let me just move on, starting from here. So using specific volume, inverse of density, you are going to substitute this concept. This is, okay, pressure change is going to create the specific volume change. Essentially doing this, compressibility, right? There's a negative sign involved in front because positive change of pressure, which is higher pressure, is involved with the shrinking of volume. It's a negative sense, that's why. If you have a lower pressure, volume expands, so it's a negative relationship. If one gets bigger, gets smaller. If one gets smaller, one gets bigger. So I just put the negative sign here. That's the only reason. Somebody was raising hand. Go ahead, please. Go ahead.
So that top equation that you used is
Top
based
equation.
on
Which equation?
that one right there. The delta work. That's based on process also, right?
Process?
That's not
Yeah,
like the
process
state
is, yeah. Right now, it could be expanded very rapidly or expanded slowly. Again, it depends on the Mach number though.
Okay.
If the Mach number gets higher and higher and higher, that shrinking expansion process gets faster and faster. So that means this is probably non-linear relationship, but let's just simplify for a moment, saying that it's very simple. If the pressure gets increased, you're going to try to shrink this whole volume by pushing this small tiny boundary dA with this much distance.
Okay.
If you integrate this small tiny areas traveling distance over all volume, this is the work. Okay, what kind of work is that? It's moving boundary work. It's similar to you push the piston to make the air inside the piston smaller. So that force you push is essentially force due to pressure. So the higher pressure shrinks of your volume. That is moving boundary 1. This is a mathematical expression for it. And let's substitute this one with the original equation of first law of thermodynamics. In other words, I'm going to substitute into here and then see what happens. Okay? Because I want to kind of model the energy transfer, okay, due to compressibility. So let's just substitute this. Well, what's the original equation? Original equation is,
It's on the bottom left.
original equation is this, right? Okay, original equation is delta Q plus delta W is equal to dE. Then I'm going to substitute into here, right? Then you're going to get this equation. Okay, so I'm going to come up with the equation 1 to begin with. Equation 1 is a substituted delta W is equal to minus PdB. So you get equation 1, delta Q is equal to dE plus PdB. Now this lowercase b is the specific volume, inverse of density. I don't talk about density. I talk about specific volume. Now, okay, so this is equation 1. Okay? Let me introduce you an interesting concept. Have you ever heard of something called enthalpy?
Yes.
Yeah.
What is it?
That's a state.
What is enthalpy? In conceptual sense. By the way, I'm HR department from Boeing. Here's my question for you. What is enthalpy? Explain that to me in conceptual sense. Oh my goodness.
I know that it depends on its power.
By the way, at least you know the equation of enthalpy. Enthalpy oftentimes use lowercase h. Lowercase typically means per unit mass because we're talking about 1 kilogram of mass. Okay, every property is divided by mass. So that actually becomes lowercase. If you have energy divided by mass, it's lowercase e, energy per unit mass. So this is enthalpy per unit mass, by the way, because this is control mass of 1 kilogram unit mass. What is the do you guys know equation of enthalpy from fluid mechanics or thermal?
CV delta T? Is that one? No.
Or original definition, two things combined to make it enthalpy.
U plus something.
E plus something, huh? E plus what? P over rho. Now, 1 over rho is lowercase b, which is specific volume. So this is E plus PB. You remember those things for fluids? Let's just go back and take a look at fluid mechanics notes then. Like I said, I don't want to rush this week. So I'm going to, okay, for a moment, let's just go back to fluid mechanics. Because lots of you say, oh, my teacher didn't cover, I don't think so. So enthalpy comes from probably unit D, talking about Reynolds transport theorem, and then conservation of energy. So it's going to be like a very bottom of this unit. Okay. So this is Reynolds transport theorem in terms of energy. Then you're going to combine with the first law of thermodynamics. Then you come up with this equation. So do you remember that? Okay. So this is the energy per unit mass for each particle is. This is actually total energy. Oh, that's kind of confusing. But U over this is called internal energy per unit mass. This is called kinetic energy. This is potential energy. Do you remember those things?
Yes.
Yeah.
Isn't it supposed to be a capital E?
I don't know. They use a different notation. Then you're going to introduce like, oh, you know, flow energy. There's something called flow work or flow energy. You have to add on to it. Then you get confused. Okay, what the heck is that? So flow energy contents coming into play. Then you come up with this equation. This is called conservation of energy. And then probably you heard from a professor, ME professor, may or may not do this, but hey, let's combine those two, you know. This is the internal energy per unit mass. This is a flow energy per unit mass. Those two combined together, this is called enthalpy H. Do you remember those? Might be like a remotely, wait a minute. My professor may have said that. I probably didn't emphasize, so I felt it's okay to forget about it. Now, all of a sudden, I'm beaten up by error professor now. Too bad. So this is enthalpy. Enthalpy is a combined property of two things. One is internal energy per unit mass. Again, in arrow, we're going to use E, but it's kind of confusing. But just stay with me, okay? Because people use a different definition for different notation. So in arrow, this is E, internal energy per unit mass. This is the same notation, pressure divided by density. And this is called flow work or flow energy. What is the flow work or flow energy? You are looking at it right now. This thing. That's the flow work. Compressibility in high speed in air. That is called flow energy or flow work. So those two combined together is enthalpy. So let's just go back to this note right here. So what you're looking at is, okay, enthalpy is combined two things. One is internal energy per unit mass. Per unit mass. This is flow work, also per unit mass. So now you know what the heck is flow work, right?
Yes.
That is essentially compressibility. You have a piece of air, keep shrinking, expanding because you're flowing high speed and pressure keeps changing. Now, if that kind of thing starts to happen, you can no longer assume it's incompressible subsonic. It's usually happening beyond 0.3 Mach number. So that's what you're seeing. Now you define enthalpy. Then let's just plug in. This is equation 2, by the way. Then I'm going to differentiate equation 2. Okay, 1 more minute. Let me just finish up this page at least. Okay. So I'm going to differentiate. Differentiate equation 2 involves, so this is dH left hand side. Right hand side is dE plus P and B combined together. So this is going to be pressure times dV plus B times dP. Okay, because pressure and the specific volume is multiplying together. You come up with that. So from here, dE is equal to dH minus PdB minus BdP. That's called as equation 3. Now let's substitute equation 3 into 1. Equation 1 back in. I'm going to substitute dE back into equation 1, where you have delta Q is equal to dH minus PdB minus BdP plus PdB. Oh, wait a minute. That means this and that drops out. So this is going to be dH minus B dP. So what do you get? Delta Q is equal to dH minus B dP. Oh, I got this equation. What kind of equation is this? This is called first law of thermodynamics. In terms of H, enthalpy. So what did we do today? I guess you get confused. Oh, okay, what did you do? It started from first law of thermodynamics in terms of internal energy, in terms of E, okay? We started from here. This is the first law of thermodynamics in terms of internal energy E. started from here, then we came up with, first law of thermodynamics in terms of enthalpy. So we have two different forms of first law of thermodynamics. You can express the first law of thermodynamics in control mass form. One is in terms of internal energy E. One is in terms of enthalpy H. So you got two equations. Basically, it's the same equation, different form. That's what we did today. So next class, what can we do from here? Let's move on, okay? So let's stop here today. Any question?
Yes. So I'm assuming we're going to be able to use this to be able to supersede the Mach 3 or Mach 3 issue.
Yeah.
But is it like just something you would add to Bernoulli's equation, or something you just check off?
Oh, you're gonna find out. You're gonna find out. I kind of hate to casually explain it so that you kind of lose the focus, sort of. So let's just keep thinking and debating yourself, saying, okay, we need something that can substitute Bernoulli. That's what you're thinking.
Yeah.
We're gonna get that, yes. But we need to visit the energy concept because more than 0.3 is a faster speed. High speed, you have to incorporate the concept of energy. That's what we're trying to do. Then you're going to get an equation that can potentially substitute Bernoulli in high speed, more than 0.3 micrometers. Okay, so we're going to get that eventually. I hate to answer casually right now because that may kind of, I don't know, take the focus away. So I'm not going to do it, but you're going to find out, I hope. I know you're unhappy, but let's bear with me. You're gonna find it. Excited. Any other question? We're gonna see you back on Wednesday. We're gonna continue exploring this.